Okay, so we continue. So we can be given terms of a series that we need to put into a summation form. So if you are asked, example, write 2/3 plus 3/5, 4, plus 4/5 plus 5/6. So if we're asked, write this using summation notation. So here we have to figure out what is happening. Okay, so when you look at this, we have say k. Remember, our k begins from 1, so we have k plus 1 over k plus 2. Okay, so that's a k plus 1. The first one, when k is 1, so this will be summation. When k is 1, we have 2/3, and it goes up to 5, so that means k goes that means we're summing up to 4. Okay, k begins from 1, but we can make our summation to begin from 0. So this is still okay, but you can make this summation also to begin from 0. So that means you take out a 1 there. So on the summation, you take out a 1. You have 1 minus 1. And then there you have 4 minus 1. Then inside here, wherever there's k, you are not taking out, but you'll be adding a 1. You also add a 1 there. This gives us summation from 3, k from 0 to 3, and you have k plus 2 over k plus 3. And that is our solution. So we have put this in a summation form. At first we began from 1, which is still okay, but we wanted to put our summation to begin from 0. So when you're doing something here on the summation, when you're subtracting, inside here you add. If you're adding on the summation, inside there you subtract. Okay, so there are a lot of examples that you can follow from the module on how to convert the terms into a summation form. Okay. Now we move to a special kind of series known as the geometric series. So a geometric series is a series that is in the form begins from 1 to infinity a r k minus 1. And the sum of a geometric series is given by a 1 minus r. Okay, so this is how a geometric series looks like. So depending on the sum here, if this is a finite number, then we say that the series converges. If it's not a finite number, then the series does not converge. Okay, so this is a1 minus r is the sum of the geometric series. Let's have some example. Find the sum of the following geometric series. So we have the first one, 3/8 k. K is equals to 1 to infinity. Then the second one, we have sum of -1 to the power k, 2/5 to the power k minus 9. Okay, so to find the first one, the sum, just rewrite the series again. So when you look at this series, remember the geometric series has to be in the form AR k minus 1. K begins from 1 to infinity. Okay, so you need to have a term which is raised to the power k minus 1. And for us to have this term, we can take out 1. Then what we're going to remain with is this k minus 1. Remember, if we have 2 to the power 4, this is the same as 2 multiplied by 2 to the power 3. But 2 to the power 3 is just the same as 4 minus 1. So this is the same as k minus 1. So when we take out 1 and multiply, what remains we are going to multiply with k minus 1, so that when you add the 1 here and the 3, you still come back to the 4. So that is why we are having another 3/8, and we're multiplying by 3/8 raised to the power k minus 1. Okay, now that we have a term that is raised to the power k minus 1, therefore we have this series is now in the form of a geometric series. So that means our A is 3/8 and our R is also 3/8, this term that is raised to the power k minus 1. And remember, the sum is just A over 1 minus R, which is 3/8, 1 minus 3/8. Okay, and the answer is 3/5. So that is the sum. Okay, so we move to the next example. Here we have sum k is equals to 4 to infinity minus k 2/5 k minus 9. Okay, so again, remember the geometric series is supposed to start from 1 to infinity, but in our case we have this starting from 4, so we have to change here. We have to make sure it starts from 1. So we have 4, we're going to do what? Subtract the what? 3. Infinity minus 3 still remains infinity. Maybe let's put it here. Four minus 3, infinity minus 3, which is 3. Wherever there's k, if we're subtracting here, inside here we're going to add k plus 3, 2/5, k minus 9 plus 3. So this will now give us k is equals to 1. Infinity minus 1 to the power k plus 3 and 2 over 5 to the power k minus 6. Okay, so we have taken the first part where our geometric series has to begin from 1. Then next we have to have a term that is raised to k minus 1. Okay, so for us to have such a term, for us to have k minus 1 here, so that means we're supposed to be adding what? A minus. So that means that we have to put in a minus 4 or a 4. Okay, so if we take out a 4 here, we want to remain with k minus 1, so we can take out a 4. Minus 1 to the power k, no, this will be 4. Then we also have 2 to the power 5 to the power minus 5. So that what remain here is minus 1 to the power k minus 1 and 2 to the power 5 to the power what? K minus 1. So when this is added to that, we have k plus 3, and when this is added to that, we have k minus 6. Okay, so 1 raised to the power 4, so this is an even number, so it just becomes a positive. So that means we have this raised to the power minus, but since it's raised to the power minus, it just means it's a it's like that. Which is just the same as 5 over 2. 5 over 2 to the power 5. And since all these have got the same terms, same power, we can just subtract, we can just multiply. Okay, so once we have it in this form, then this is the form of a geometric series. This is our A, and this is our R inside there. So our A is 5 over 2 to the power 5, and our R is minus 2 over 5. Okay, so that means our S, of course we know it's A, 1 minus R, 5 over 2 to the power 5 over 1 minus, so it's a plus 2 over 5. So find that on the calculator, and the answer should be 15625 over 224. Okay, so that is our solution. Okay, so here we're just finding how to find the sum of a geometric series, and we've gone through those examples. So make sure your series is in form of a geometric series, that is k beginning from 1, then you have an A, you have R raised to the power k minus 1. Okay, so the next thing that we're going to move to is actually the convergence of a series. So we have different tests that we use for the convergence of series. The first one is the alternating Okay, so before we look at an alternating series test, we just have to remember that an alternating series is a series whose terms alternate between positive and negative. Okay, a series, say maybe this one, let me write in summation form. Okay, so in this case, you have A1 minus A2 plus A3 minus A4 plus goes on. So whenever you have this term, the 1 minus 1 raised to the power something, then you know that that series is alternating. Okay, so you can see you have a positive, then negative, positive, negative, positive, negative, and so on. So these are alternating series. Okay, now the alternating series test, we move to that. It just says that an alternating series converges if the following conditions are satisfied. A1 is greater or equal to A2, greater or equal to A3, is greater and goes on. And if the limit of an is equals to 0. So if the limit of an is equals to 0 and the series is decreasing, then the alternating series will be said to be convergent. Okay. Then let's also state the divergence test. Okay, so this one just states that if the limit okay, so maybe let's do this. An alternating series diverges if limit n goes to infinity of an is not equal to 0. Okay, so if the limit of an alternating series is not 0, then it is said to diverge. So if it's 0 and it is also decreasing, then it is said to converge. So let's have some examples. Determine if the following series is convergent or divergent. So the first thing is first to find the limit. So an here is just 1 over n. Now let's find the limit. N goes to infinity over 1 over n. We know this is 0. Okay, so the second condition is satisfied. Now we just have to check whether it's decreasing or not. So A1 is just 1, A2 is 1 over 2, A3 is 1 over 3. So we see this case. So that means that our series is convergent by the alternating series test. Okay, so that's done. Let's go to the other one where we have sum minus 1 n plus 1 n squared plus 1 over so let's just rewrite that. Okay, so in this case, again, let's first find the limit. We know that an, so an doesn't include this first part, the minus 1 to the power n plus 1, no. An is just what follows, n plus 2 plus 1 over 5n squared plus 2. Okay, so this is our an. So let's find the limit. N goes to infinity of an. Now when we replace there, we see that we have a case of infinity over infinity. So we just divide by the highest power of n. Okay, so this when we have this n squared over n squared, it will cancel. Just have what? And this part is a 0. This part is also a 0. Then that's just a 5. So we have 1 over 5. And this limit is not equal to 0. So if it's not equal to 0, we can't use the alternating series test. But we now use the divergence test. So if the limit of an alternating series is not equal to 0, then we conclude that it is divergent. Okay. Alright, so now we move to the next thing. And that's just a definition of absolute convergence. So this one just says that a series converges absolutely if the absolute values of each term converge. So if the terms, each of the absolute value of the terms converge, then the series will also converge absolutely. And we also have conditional convergence. Conditional convergence is a case when sum of an converges, but the absolute value doesn't converge. So if we have the case where an converges but the absolute value of an diverges, then the series an is said to converge we say it's to converge conditionally. Okay. All right. Then we move to the other test that we used for convergence, which is the p-test. Now this is a p-test for series. So this just means that a series n raised to the power p converges if p is greater than 1 and diverges if p is less or equal to 1. So let's have an example. Okay, so if we look at this series, using the we actually found that this series, we're using the alternating series test. This series was convergent. Okay, the series was convergent using the alternating series test. Okay, so this was convergent, but now let's check its absolute value, because if we use the absolute value, then we're going to get rid of this part and we're just going to remain with 1 over n, which we can now use the p-test. Okay, so when we get the absolute value, we know the absolute value of minus 1 is just 1. We get 1 over n plus 1. Now, according to the p-test, our p here is what? 1. So that means this is divergent. Okay, so that means the series an is convergent, but its absolute value is divergent. That, remember from the definition, this just implies conditional convergence, where an converges but its absolute value diverges. So we're going to conclude that this series converges conditionally. Okay, so we now move to the other test, the comparison test. Actually, when you just look at the comparison test and the p-test for improper integrals and series, the rules are actually very similar. They are very similar. So in the comparison test, we have that, the first one. If an is less than bn and the series bn is convergent, then an is also convergent. Okay, so this one just states that if you have a bigger function, the function that is big is convergent, then the one that is smaller will also be convergent. And the other rule is that if you have a smaller function, Bn is smaller, is less than An, and the series Bn is divergent, then An okay, so that's the test, the comparison test. So if the smaller function is divergent, even the bigger one will be divergent. If the bigger function is convergent, even the smaller one will be convergent. Bigger one is convergent, the smaller one will be convergent. If the smaller one is divergent, then the bigger one also be divergent. Yeah. So example. Let's have this. The sum 1 over the cube root of n minus 1. Okay, so we can compare this to 1 over n and 1 over. So which one is, so if we take for n is equals to 8, which has a cube root, so the cube root of 8 is 2 minus 1, say 1, so here we have a 1, and here you have 1 over 8. So that means this function is bigger. So the unknown function is a smaller one. So is this divergent? Now using the p-test, n is 1, I mean p is 1, that means this series is divergent. Okay, so if the smaller function is divergent, it just means that the series the cube root n minus 1 is divergent, or I can say using the comparison test. Okay, so that is how we use the comparison test. There are some examples that we can follow. This is how we use the comparison test. So we're just remaining with 2 more tests. So the next one is the ratio test. So all these are used to test the convergence of series. Okay, so we now move to the ratio test. So in the ratio test, we have that if we have a series, which has a limit such that this limit is obtained by getting the modulus of an plus 1 over an. Then L yeah okay, yeah, so that is the, this is our limit, then L, if L is less than 1, then the series converges. Okay, and if L is greater than 1, then the series L is greater than 1 or L is equals to infinity, then the series diverges. Okay, and if L is equal to 1, we cannot say anything about the convergence or divergence of this series. Okay, so this is the ratio test. Some examples from the book, from the module, which we can follow. Okay, then the last test is the root test. The root test, where we have a series, we have an, and we have the limit such that this limit is obtained by taking the nth root of the modulus of an. Then the series is said to converge if L is less than 1, and if L is greater than 1, then or L is equals to infinity, then it diverges. Okay, if L is equals to 1, then we cannot tell the convergence of the series. Okay, so, and again, I think the examples from the book are easy to, from the module are easy to follow. Okay, so thank you so much, and we're going to end here. All the best.